Okay, this is the reaction rates lab that we're working on, and we're doing the first demonstration, which is to take 50 milliliters of hydrogen peroxide and to add a catalyst to that, and that is manganese dioxide. So I already have my 50 milliliters of hydrogen peroxide here, and I'm going to take my 1 gram of manganese dioxide, and you need to watch what happens when we add the catalyst to this hydrogen peroxide. All right, so something happened. It was a decomposition, and so we're going from hydrogen peroxide to water and oxygen. So you need to write down your observations, and I'll tell you right now, this is very warm. So hopefully that'll tell you the type of reaction that we're dealing with here. And we now have all this lovely vapor coming off. And because this is a catalytic reaction, the solution here has turned black because our catalyst is black. There wasn't a chemical reaction to make it turn black. That's just the color of the catalyst. But the catalyst is still good. So if I were to add more hydrogen peroxide to this, it would still react. Just to give you an idea, I'm going to go ahead and pour a little bit just so you can see that it is still active and it will decompose more hydrogen peroxide. And that'll keep going invariably till the hydrogen peroxide runs out. All right, so there is our first demonstration of what we expect to see in these lovely rates. And so you can see this one is relatively quick. We don't time it per se, but we did make that happen. So there is our first. The 6 molar with the magnesium here. So we'll go ahead and get these at the same time. So let's go ahead and start pouring this in and hit start. Let that go and let that go. It's reacting quite nicely. And I'm going to say we're done. Okay, 14 seconds or so. So there we have a lovely reaction with our magnesium and our 4 molar hydrochloric acid. We're going to go ahead and time that reaction. So here we go. As long as the bubbles are going, it's reacting. It's taking longer than the 6 molar. And we're getting close to the end here. We're having some of the bubbles. There's still some bubbles there, and looks like almost there. See a few more bubbles there. Keep going, we're almost done, and I'm gonna call that good. Okay, so I have 38 seconds and 73 hundredths of a second. All right. So let's go ahead and do the last one, which is gonna be 2 molar. There's 3 milliliters of this as well. So we'll go ahead and put that in here. So let's just start over. So 3873, and then here we go with the last one. As soon as that hits, we're gonna hit the button. Okay. So now we're watching that react. You can see all of the bubbles produced there. So I feel that this is an opportune time to let you know about the world of terrible jokes in chemistry. They all have a purpose, of course, but they're not necessarily all sterling examples of humor. But one of my favorites has to do with 2 hydrogen atoms. They walk into a bar, and one says to the other, "Hey, I think I just lost an electron." The other one says, "Are you sure?" He says, "Yeah, I'm positive." Yeah, it's okay. They're never good. It's just something. So we're doing really well here. We're getting close to a minute. We're still running. Hopefully you can see those bubbles still being produced. Still trucking. have been enjoying the no laugh zone because that was the terrible joke that I told. But there we go. We've got that lovely solution working, and it's still bubbling. Still got some bubbles going on there. For that bubble ring to stop so that we can say that it's completely reacted. And what we're hoping in all of this is that our limiting reactant, still warm, it's pretty nice there, is the magnesium. There's still acid in there, and so we're real close there. Still got some bubbles going. Real close. Getting close to the 2-minute mark, and let's go ahead and call that. So a little over 2 minutes, 2 minutes, 1 second, and 82 hundredths of a second. So there we go. We've got the 4 molar and the 2 molar, and we're gonna have to hydrochloric acid. So hopefully you can see that the stronger the concentration, the faster the reaction took place, and it wasn't necessarily a linear relationship, because this was 13 seconds, this was 38 seconds for this one right here. This one was a little over 2 minutes. So it's not necessarily a linear relationship. It might be exponential, probably, based on our understanding of how this math works. So that's exciting for Okay, so we're going to do temperature variations using the potassium permanganate, KMnO4, and sulfuric acid as our setup solutions. And so this water is at about 40 degrees, just shy of 40 degrees Celsius here. And then we'll also do this water over here. We'll put that in there and you can figure that out. So what I'm going to do is I'm going to take this. This is 15 drops of, this right here is 15 drops of potassium permanganate, 10 drops of water, and 15 drops of sulfuric acid. I'm gonna go ahead and put it in this water bath here. So it's gonna heat up. And then if we look at this cold bath here, it is down around 8 degrees at the moment. So we are doing well here. It's probably gonna chill just a little bit more. We'll come back to that. And we'll put this same exact setup there. So what we're looking at is how the temperature of the solution affects the rate of the reaction. So we have both of these ready to roll. This thing is at room temperature, which in this room is about 25 degrees. And so what we're gonna do is we're gonna add this oxalic acid to those solutions and try and watch what happens as the reaction takes place. So here is our room temperature compound, and we're gonna go ahead and add the required 5 drops of oxalic acid, and then we're going to also time it, how long it takes for it to react. So I'm going to go ahead and get my phone out and have the timer going. Now the numbers are going to be reversed, so you're going to have to take my word for it, but here we go. Have my phone, try and get it so the digits are visible. And we'll watch as we add the oxalic acid. So here's our reaction mixture, and we'll go ahead and start the time as soon as we get done adding the oxalic acid. So 1, 2, 3, 4, 5 drops. Go ahead and hit start. We're gonna watch it, and hopefully the color will disappear on us. Just agitating it a little bit to make sure. So it should go from that lovely purple color to a clear color. So we're just agitating it just to make sure that we are getting full reaction, and you should start seeing it getting a little lighter as we look through all of this. And that looks good to me. So we're gonna hit stop. All right, so 38 seconds, more or less, it took for that to disappear. Okay. So that's room temperature. Now, hopefully you have an idea of how this is all going to work. So next we're going to look at our solution here that's at 8 degrees. See if I can get that where you can see it. So we're at 8 degrees. Ooh, looks like, yeah, between 7.5 degrees Celsius. So we're going to go ahead and put our oxalic acid in, the 5 drops. and we'll see what happens. So 1, 2, 3, 4, 5, and we'll go ahead and start over. And we'll just leave it here so you can look at it. And we'll wait for the color to disappear on all of that. We'll start getting the temperature of our hot or warm, and we'll watch this go. So my guess is it's going to take a little bit longer, so we should go well past the 38 seconds that we had prior to this. It's going to interact and react and have all sorts of fun things taking place. So just for your procedural part of this, just so you can write it down. So we put in our 15 drops of this potassium permanganate, and we added 10 drops, of distilled water. Then we added 15 drops of sulfuric acid. And then for each of these, we have this in a cold bath. So there was ice in here, but it's melted. And that's why its temperature is down around 7.5 degrees Celsius. We had the room temperature one that we left on the counter where we started. And then we also had the warm bath, which is, at this stage, it's down around 33. So we'll get that when we start it again. But you hopefully should see that the color is starting to go down. We'll go ahead and shake that on this. So it's still pink, but the color intensity has gone down. We can compare it to this one over here, which is just a little bit more intense. It's still pretty good, but it is starting to lessen a little bit. And what I may do is I may take this over there and go warm it up so we can get back to close to 40. We're supposed to do it at a warmer temperature. Okay, so I'm warming that up while we're still waiting for this to disappear. So you can see we are still pink as we look at that. So we'll leave it in that bath so we can keep that temperature constant and keep on trucking as we wait for this reaction to finish. So we're about 2.5 minutes right now. So we're doing really, really well. Oh, getting real close. It's just a little bit of pink left. Let's hold it against this paper. It's still pinkish. You can see that. We'll keep it in the water bath. And you know what? I'm gonna call it. That looks pretty done to me. So we're gonna say it's done at 2 minutes, 50 seconds. All right, so now we're gonna do the last one. So I'm gonna go get it off the heater and we'll see what temperature it's at, and we will look and see how fast the warm one will do. So here we go. Here is our last temperature one. So let's see where our temperature ended up. Oh, very nice. We are at 45 degrees. So we're gonna go ahead, take our thermometer out. We're at 45 degrees. This has been sitting in the water, and we're gonna go ahead and put our 5 drops. So I'm gonna reset this and see how fast it's gonna go. 1, 2, 3, 4, 5. And we'll start it. And it's going pretty quick. And we're done. Okay, so 11 seconds, 10.93. So 11 seconds is all it took for that at the 45 degrees temperature. So just to reiterate so you can know what we're expecting here, the room temperature one was 38 seconds. The cold temperature at 7.5 degrees Celsius was 2 minutes and 50 seconds. And then the warm one at 45 seconds was, at 45 degrees was 10 seconds. All right, so well done. That's the end of that experiment. So go ahead and graph your data and hopefully be able to see how that all works out. All right. Okay, so we're on to the next experiment here. So we're looking at an iodine clock reaction. So what's happening here is we're generating iodine by mixing sulfuric acid, H2SO3, with iodic acid. And it will cause a compound to be made, it's an ion called I3-. And when it comes in contact with starch, which is in this lovely beaker here, it makes a lovely blue-black color. So the first experiment wants you to take 2 milliliters of the iodic acid and mix it with 5 milliliters of the sulfurous acid. So before you can mix these two, though, it says to put 2 drops of starch into the beaker here. And so here's my starch solution, and I'm going to go ahead and see if I can get myself 2 drops of it. So I'm going to go ahead and put 2 drops of starch in there. I'm going to mix it up real nice here. And then I'm going to pour into this one so you can see a little bit better about what happens. So I want to keep the time of this just for the sake of discussion, and just go ahead and I'm going to pour this, and this would be a 2-man operation, but generally, oh, can you see that? It turned a nice blue-black color, and it should go all the way through, but I guess we didn't mix it up very well because we were in the smaller test tube. That's the coloration that we're looking for when we do this. That went really quick, and we didn't really get a sense for that. So what we're looking at here is we have set up a series of reactions. I need to find some place to put this. There we go. And so in this test tube right here, I have 1 milliliter of the iodic acid and 4 milliliters of water. And here I have 2 milliliters of the iodic acid, 3 milliliters of iodic acid, 4 milliliters of iodic acid, and 5 milliliters of iodic acid. And then I've filled this up with 3 milliliters of water, 2 milliliters of water, 1 milliliter of water, and then this is just the pure stuff. And then behind here, I have measured out the same amount of the sulfurous acid for each of these. Maybe it's going to take longer, in which case I'm okay with that. Take some time. Oh, you know what I didn't do? I didn't put in the starch solution. Shame on me. All right, I'll have to fix that right quick. Actually, you can see this is what it looks like if we don't add the starch, right? And this is what it looks like if we do add the starch. So you can answer for yourself, what purpose does the starch serve? Right, here's the starch. Here's the no starch. What purpose does the starch serve? It is an indicator. Yes, that is correct. All right, so I'm gonna have to, okay, round 2. So actually we're gonna start with this one right here. This is just iodic acid. And so there's 5 milliliters of the 0.02 molar iodic acid, and we're gonna add the sulfurous acid to it and see if we can make it that blue-black color, but we'll make sure that we add our indicator because that's gonna be really important. Okay, so we'll go ahead and add our 2 drops of that stuff. Okay, so there's our 2 drops of indicator. All right, so let's get our business ready to go. And ready, set, start. Okay, that was 2.98 seconds to go from the lovely coloring of clear to blue-black. So that was the 5 milliliters of iodic acid. Okay, so let's go ahead and add our starch to each of these subsequent ones so we can make sure that we get them in there. So here's 1, 2, 1, 2. Some more starch here. 2 and 1, 2. Okay, so we've starched them all. Lovely. Now we're going to go ahead and try the next one. So here is 4 milliliters of iodic acid and 1 milliliter of water. And we're going to go ahead and mix and start. So mixing and starting. And wow, that was quick. So that was 3 minutes and 3 seconds. Okay. So we reset that. Now we're next to the next one. This is 3 milliliters. Okay, ready, set, start. 3 minutes, 40 seconds. Okay, 3 minutes and 41 hundredths of a second. Okay, make sure these are all nice and mixed here. Reset, mix these and push the button, and here we go, we're starting. And that's 6 minutes 6.65 seconds for that one. Okay, 6.65 seconds. And then here we go, last one. This has got the least amount, so it should go the slowest. So here we go and start. Turn it, we'll see it move. Looking, we're waiting. There it went at 19.43 seconds. Okay, so at the front end, they were very quick, and then they tapered off towards the middle, and that's because there was less iodic acid. So hopefully we'll be able to run through that data and be able to determine the order of the reaction. And so that's going to be set up for you as you follow the lab. It's going to have you mangle the data a little bit and force it to fit into a straight line. And then you're going to find the equation of that line, and that equation of the line will fit the equation in your lab so that the log of the rate is going to be equal to n, which should be the order of the reaction, times the log of the concentration plus the log of the equilibrium constant that we're going to look at. So when you have that equation of the line, you'll have to take the anti-log, or 10 raised to that value that you have on it, to determine the value for the equilibrium constant. So hopefully with the slope of the line, we'll figure out the order of the reaction, and you can be able to figure out how to write out the answer for that. Okay, happy graphing.